All right, so in this video I'll continue the test for review. Here in number 5 it says sketch each function by first graphing its parent function, which I think sometimes people call the basic function, then using shifts and or reflections to draw its graph. So for letter A we have f of x is equal to e to the x plus 2 minus 3. And so first of all, we want to graph the parent function, which would be y equals e to the x. And so this is an exponential function, and so I'm going to choose x to be negative 1, 0, and 1. Of course, e to the 0 power would be 1. If you plug in 1 for x, y would equal e to the first power, which is e, which is about 2.7. Again, you could find that on your calculator. And e to the negative 1 power is 0.4. So I'm going to go ahead and graph this function. Those are the 3 points. We know the exponential function goes through the point 0, 1 and has an asymptote at y equals 0. Whoops. And hold on just a second here. It looks like that. So I did make that dotted because that's not our final answer here. Now notice, because we have e to the x plus 2 power, that plus 2 is going to cause a horizontal shift, so we'll go left 2. And the minus 3 is separate from the function. It's going to cause the graph to move down 3. And so I'm going to take each of the 3 points that I have, and I'll move them down 3 and left 2. Now when I go to the left, that won't change the asymptote, but when I go down 3 it will. So it'll be right there at y equals negative 3, and our graph will look something like that. Now I didn't ask you this, but I'm going to go ahead and do this. You should be able to tell me what the domain and range of this function is. So the domain, as is the case for exponential functions in general, is all real numbers. And the range, in this case, we don't quite get to negative 3, so it'll be parentheses negative 3 to infinity. All right, so let's go ahead and move on to b, which is g of x is equal to 3 minus the log base 2 of x. And I actually prefer to write it this way. G of x equals minus the log base 2 of x plus 3. The key is you have parentheses around this x to indicate it's not the log of x plus 3, it's the log of x, and then you're adding 3. And so let's go ahead and graph the basic function, or the parent function, which would be y equals the log base 2 of x. And again, it's easier to put this in exponential form and then choose our points. And so this is 2 to the y power is equal to x. So we're going to make a table. And again, we're going to want to choose our y values to be negative 1, 0, and 1, which is the case with logarithmic functions. That's what we tend to do. And so now when I plug in 0 for y, I get 2 to the 0, which means x would be 1. If I plug in 1 for y, you get x equals 2 to the 1 or 2. And if you plug in negative 1, you get a half. Again, these two numbers will always be reciprocals. So let's go ahead and plot those points. And this has the basic shape of a logarithmic function. Notice it goes through 1, 0. It has an asymptote at x equals 0. It looks something like that. And again, this is the basic function, so I'm going to make it dotted. Now, because of this minus in front of the log base 2 of x, we're going to have a reflection through the x-axis. And because of the plus 3 at the end there, this is going to be a vertical shift up 3. Now with reflections and shifts, we normally will do the reflections first. And so let's go ahead and reflect these 3 points through the x-axis. And in fact, the graph's going to look like that. This is the graph of y equals minus log base 2 of x. So again, we're almost there, not quite there. We need to move up each of the 3 points up 3. And so I'll go ahead and do that. Notice the asymptote won't change when I move the points up 3. And so it's just going to be where it was before. So there's your graph. And if you're looking for the domain here, which I would encourage you to try first, the domain is 0 to infinity. And the range is going to be all real numbers. There is no lowest or highest point. All right, let's look at number 6. It says global wind power capacity is increasing exponentially. The total capacity in gigawatts can be estimated with the exponential function, as you can see here. Well, it's WT equals 29.9 times 1.26 to the T power, where T is the number of years after 2002. Find the global wind power capacity in 2005. So if we're finding the global wind capacity, we're finding W a T. And in this case, they're giving us T because they said it's in 2005. So T is going to equal 2005 minus 2002, or that's 3. And so we want to find W of 3. And so when you plug 3 into the function, you should get 59.8. And again, this is the capacity, which is what W of T represents, is in gigawatts. So it's 59.8 gigawatts. All right, let's move on to the next slide. So it says, find each of the following. Do not use a calculator. Show your work. So on the test, you'll be asked to show your work. And what I would be looking for is the following. So on A, it says log base 4 of 16. Now we discussed the fact that a logarithm represents an exponent. This logarithm is the exponent you put on a base of 4 to get an answer of 16. Well, 4 squared is 16, so this is 2. In fact, I taught you this little around the world thing. 4 to the second power equals 16. And that's exactly what we have here. All right, so if you haven't already done the other 4, I would encourage you to do so. So on B, this logarithm is the exponent you put on a base of 4 to get 1 over 64. Now, hopefully you recall that 4 cubed is 64. So we know that 4 to the negative 3 power would be 1 over 64. And so our answer here is negative 3. On letter C, 2 to some power is 32. You may have to look at your powers of 2, but that ends up being 5. On letter D, you could write this as log base E of E. So the question is, what exponent do you put on a base of E to get E? Of course, that would just be 1. And then on letter E, what exponent do you put on a base of 16 to get 4? Now this one's a little bit tricky. You've got to remember a rule of exponents that we've discussed in the past. Namely that if you have some number or base to the 1/2 power, so x to the 1/2 power, for example, that's equal to the square root of x. And so 16 to the 1/2 power would be the square root of 16, which does equal 4. So the answer here is a half. 16 to the 1/2 power is equal to 4. All right, in number 8, it says use the change of base theorem to evaluate to 4 decimal places. Show at least one step. Well, we're going to use the change of base formula or theorem. This is equal to the log of 38 over the log of 5. Now notice how I put in the parentheses, especially this one here. It's really important that you put that in when you plug this into your calculator. And basically, the way I see it is it's the log of the larger number over the log of the lower number. Notice these new logs are base 10 logs, or what we call common logs. And now when you plug that into the calculator, you should get 2.2602. And the thing to remember is this logarithm is the exponent you put on a base of 5 to get 38. So you can always check these if you have any doubt at all. 5 to that power, 2.2602, should equal 38, and you can verify that it does. One of the reasons why we go to 4 decimal places is just so that when you check it, you can see that it's accurate enough that you believe that's the correct answer. It is a rounded answer though. All right, on B, this would be the log of 24 over the log of 3, and you should get 2.8928. And again, you can check this by saying, okay, 3 to that power should equal 24, and you can check that that's the case. On letter C, this is actually going to be quick work here, because we learned when we were graphing logarithms, the basic logarithms, the domain was positive numbers. It had to be greater than 0. The log of a number, when you're taking logs, you cannot take the log of 0. You cannot take the log of a negative number. And so this, we would say, does not exist. Basically, negative 8 is not in the domain of the function if you had y equals log base 8 of x. So we can't take the log of a negative number, so we just write DNE for does not exist. All right, now for number 9, it says write each expression as a sum, difference, or product. Simplify the result if possible. Now, the word I used for these is we're going to expand these. They're currently single logs, and we're going to expand them until we have logs of a single value. Now, we have 3 properties that we use when we do this. I'm going to go ahead and put these up here. The first one is the product rule, because it's the log of a product is equal to a sum of logs. The second one is called the quotient rule, because the log of a quotient is equal to a subtraction or a difference of logs. And the third one's called the power rule, because we're taking the log of some base to a power, and we can move that power out front. So if you look at A, you can see that we have 3 times x times y squared. We have a product here, and we also have a power. Now you don't have just excuse me. If you look at rule 3, it's a single base to a power. M is your base. That's not what we have in this problem. The 3x is kind of in the way. So I can't use the power rule yet, but I can use the product rule. That's rule 1. And so we can break this into 3 sums, or the sum of 3 things. Log base 4 of 3, plus the log base 4 of x, plus the log base 4 of y squared. And then hopefully you look at this last term and you realize you can use property 3 there. And so this becomes the log base 4 of 3 plus the log base 4 of x plus 2 times the log base 4 of y. All right, let's move on to B. So again, if you look at B, you actually can see that we're going to use all 3 of our properties here. We certainly have a power here, or an exponent, so we'll use the power rule. The problem is I can't just ignore this denominator and move the 5 out front. And what about the y squared? So we don't have a single base to a power. I can't use the power rule. I also can't use the product rule because I can't just ignore that I have a numerator here. So the only one that I could use is the quotient rule. We do have a quotient of 2 things. And so this is the log of x to the 5th minus the log of 10y squared. We're just using property 2. And so now notice here we have a product. Now I am going to use the power rule here, but I'm just going to do that at the same time because I'll be using it for that y squared also. But first I'm going to use property 1 to break that product into 2 logs. So it's the log of x to the 5th power minus, it'll be the log of 10 plus the log of y squared. Now notice we're replacing one log with 2, and there's a minus in front. Well, that minus is going to affect both of the terms. So I can put parentheses here, or I could have just wrote them both with a minus. Excuse me. So now let's go ahead and distribute. We get minus log of 10 minus the log of y squared. And now we can use property 3 and we'll move those exponents out front. This becomes 5 times the log of x. Now notice the log of 10. Hopefully you look at that and you're like, I think I might be able to do something with that. Log of 10, remember the base is not written, so it's understood to be 10. So this is the exponent you put on a base of 10 to get 10. And of course that would be 1. And so this is minus 1. And then let's move that 2 out front on the last logarithm there. And you get minus 2 times the log of y. All right. Now C kind of puts together a lot of things, and it uses all 3 rules as well. I would challenge you to see if you can do that problem. If you can do that one, you should be able to handle pretty much anything you're going to run into on our test. So, So let's go ahead and look at C. So the first thing I hope you realize is you've got that square root there, and you really can't get to anything underneath the radical until you get rid of the radical, because we don't have a property of logs for radicals. And so we do know that we can write this, though, using what's under the radical to the 1/2 power. And see, now I can get rid of that 1/2 using property 3, or the power rule. So we get 1/2 times the log base b of ab to the 4th over c cubed d squared. Now, next, we have a quotient here. Again, you do have product, but you have a product in the numerator and denominator. And again, you can't just pretend that you don't have that other one there. And again, we have powers, but you can't use the power rule because you don't have a single base to a power. So the only thing I could do here, is use the quotient rule. And so you get 1/2 times the log base b of a to the 4th minus the log base b of c cubed d squared. And again, we're replacing one log with 2. And so that 1/2 is going to have to be distributed. So I'm going to go ahead and do that. And the same type of thing is going to happen when I use the product rule here and here. And so I'm just going to go ahead and distribute the 1/2 and the minus 1/2 when I do this. So the log base b of a, b to the 4th, is equal to the log base b of a plus the log base b of b to the 4th. And we'll have 1/2 in front of each of those. So we're using property 1. So the log 1/2 the log base b of a plus 1/2 the log base b of b to the 4th. And then minus 1/2 will be distributed. Again, when we break this into 2 logs, it'll be the log base b of c cubed plus the log base b of d squared. But we have to distribute that negative. And so we're going to get minus 1/2 the log base b of c cubed minus 1/2 the log base b of d squared. In fact, you may want to do that in between step just to make sure you're clear on what I just did on that step. And then, let's see, we've got one more step to go here. We've got all those powers. We're going to want to use the power rule. The first one there is just 1/2 log base b of a. That's not going to change. But on the next one here, notice, actually this one's kind of a special case here. I'm going to do this over to the left. You have 1/2 times the log base b of b to the 4th. We can move that 4 to the front, and it'll be 4 times 1/2. 4 halves is 2. So we get the log base b of b. But the log base b of b, remember, that's the exponent you put on a base of b to get b. And so that would just be 1. So this is 2 times 1, which is just 2. And so all of that simplifies to 2. On the next one, we're going to multiply by 3 there. We'll get minus 3 halves times the log base b of c. And then finally, we'll multiply by 2 times a half. And that's just 1. 2 halves make 1. And that'll become minus log base b of d. So you just got to really take it one step at a time with a problem like this and just be careful with your steps. All right. Let's go to the next page here. Actually, yeah, I think we'll stop right here.